So sorry to kind of throw this review at you last minute, but if you're having a hard time, at least you've got this. It's not a lot of the hard stuff that we've been doing. It's more kind of the basics. So if you remember Friday's like exponent rules, that's really what most of this is. So skip ahead in the video if you need to find anything particularly, but I'm just going to go through them kind of one at a time. It shouldn't take that long, I don't think. So 1 through 4, just kind of the rules that we mentioned in our notes we took on Friday. When multiplying powers, you what? So that means multiplying powers is something like number 10. Here, let me get this thing working. Here we go. So multiplying power is something like number 10, where you have some exponent to a variable times another, or not a variable to some exponent times another variable to that exponent as well. So when you have something like this, you would add the exponents. So when you're multiplying powers, thus the multiplication symbol, you're actually adding the exponents. And the reason, again, is because the exponents are just there to count the variables you're multiplying. So this says that you have 6 a's multiplied together, and then you're multiplying 3 more a's with it. So for number 10, that would be a to the 9th. Because 6 and 3 make 9 a's multiplied together. When you divide powers, you subtract exponents. And the reason for that is something kind of like in number 12. You can see that we're dividing these powers or dividing these terms. But when we're doing that, we're just sort of canceling things out. So in number 12, it says that you have 3 f's on top and 1 f on bottom. And as you know, anything that's the same as top on bottom, those things cancel out and leave you just with 1. Like 5 over 5 cancels out because 5 over 5 is just 1, right? So f over f is just 1 that cancels out. So you're left with just 2 f's, f to the second power. And of course, you can see that because if you take 3, so let me write this a little bigger. If you take 3 and subtract 1, then 3 minus 1 is 2. So f to the second power. So you're just subtracting the exponents, but I like to think of it more as canceling out. Number 3, when you have a power raised to another power, you multiply the exponents. So that's something like in number 14. You have x to the second to the 7th. This is going to end up being x to the 14th power. Because again, so what you're saying with this is you're having x squared 7 times. So there's twice, there's 3 times, there's 4 times, 5 times, 6 times, 7 times, which if you count them all up, that's 14 x's. So basically you have 7 groups of 2. That's kind of what's happening in the problem. But the shorthand way of remembering it is that you just multiply the exponents. Pretty simple. Why I can't erase that. There you go. All right, number 4. When you have powers of a product or quotient, you distribute the exponents. So that's kind of like I would need to scroll down here. So that's sort of like number 15. So again, this doesn't work if there's any plus signs or minus signs in those parentheses, but there's no plus sign or minus sign, so you just distribute the exponent. So everything inside these parentheses is getting raised to the 4th power. So x to the 5th to the 4th power would become x to the 20th. Y to the 1st to the 4th power would become y to the 4th. And z to the 2nd to the 4th power would become z to the 8th. So basically, it's the same as the rule that we just looked at before, where we multiplied the exponents, but you're multiplying it to all the pieces that are inside there. And again, that's pretty much it. That's straightforward. In number 5, which is equivalent to what you're seeing here. So notice the property that you use. Here you're multiplying powers, which means when you multiply powers, you add the exponents. So the only option that says add is A. If you can't tell, it might be hard to read, but in D, that's a division sign, not a plus sign. And they can kind of look very similar if, given the fact that it's that small. So number 6 and 7, 8 and 9 are all very similar. But 8 and 9 are the opposite of 6 and 7. So you're just going to put 6 and 7 into radical form. So what I mean by that is we talked about the radical. So if this is my radical all I would do to put in exponent form is keep the base and write these different values here is the exponent. So m is my numerator, n is my denominator. That's the exponent for a. So you're just going from one form to another. You're not really solving anything. You're just sort of rewriting it a different way. So in number 6, we have the exponent form, so we're going to write it in radical form. So if I go back to that thing that I just wrote, nth root a to the m equals a to the m over n, then notice the 6 is my denominator. So that's the quote n value there, which means 6 is my root. So this would be 6th root of x to the 5th power. The 5 is my numerator, and my numerator would be my little exponent here. Okay, so 6th root of x to the 5th. Number 7, it's x to the 1/2 power, so same idea, so radical. And the denominator 2 is my index number, and then the numerator is my exponent. So 2nd root of x to the 1st, which is the same thing as just the square root of x. So really, you should just write the square root of x. Just remember, so square root is the same as having an index of 2 or not having an index of 2. If you don't see the index number there, then the index number is 2. But of course, you don't have to write it there. You can just leave it invisible if you want to. But it still means the same thing. So square root of x, same thing. So number 8 and 9 are the opposites. They're going from radical form back into exponent form. So this would be f, and then 2 would be my numerator. So this would be f to the 2nd power over 3 is my denominator. So f to the 2 over 3 power. So f 2 over 3 is the exponent. Just make it look a little bit better. And for number 9, people get this confused all the time. So remember the index number there is 2. This is really the 2nd root of a to the 6. So if you remember that, then this would be a to the 6 over 2, which 6 over 2 simplifies to 3. So just a to the 3rd. All right, we already did number 10, but I'll say it again in case you just skipped ahead in the video and didn't pay attention to what I did in the beginning. But number 10 is the same thing number 1 is talking about, which is just the when you multiply powers, you add exponents. So if you missed it, this is a to the 9th. That doesn't look like an a to the 9th. A to the 9th power. And if you want to rewind and watch the very first part of the video, I'll explain why that's a to the 9th, but I'm not going to do it again. So you do the same idea here in number 11. You have multiplying power, so you're going to add the exponents. So that's just 7 plus -3, or same as 7 minus 3. And 7 minus 3 is just 4, so it's f to the 4th power. In number 12, again, I explained why. So if you just skipped ahead and missed it, go back and look at when I talked about number 2. I talked about number 12 at the same time. When you divide powers, you subtract the exponent. So this is f to the 3rd over f to the 1st. So 3 minus 1 is just 2, which makes this f to the 2nd. Number 13 is the same exact thing. So subtract the exponents. Be careful because you are subtracting a negative. So if you do 5 minus -6, it's really 5 plus 6. So this is the same as q to the 11th power, because 5 plus 6 is 11. All right. And again, another way of thinking about it is we talked about before that if you have a negative exponent, it means that q is in the wrong place. If you have a negative exponent, it means you need to take this base and move it to the other part of the fraction. So it's in the denominator now. It's supposed to be in the numerator. If it has a negative exponent, that's what it means. Negative exponent means you have to move it. So if you move that q up here, then it will have a positive exponent. So now you can see 5 plus 6, a little more obvious. 5 plus 6 makes 11. So q to the 11th. That's another way you can think about it. Number 14. If you skipped ahead in the video, we talked about number 14 when we did number 3. So number 14 is when you multiply these exponents. We've already mentioned that. That's x to the 14th power. We did number 15 already as well. So that's when I explained number 4. You just distribute the exponents. So x to the 20th, y to the 4th, and z to the 8th. And number 16, so you simplify these in parts. So you'd have the cube root. Whoops, wrong thing. You'd have the cube root of 8 you'd have the cube root of x to the third and the cube root of y to the second. Now the cube root of 8, we talked about perfect cubes before. So 1, 8, 27, 64, 125. We wrote this list down in our notes, but these are perfect cubes. That's 1 to the third power, 2 to the third power, 3 to the third power, 4 to the third power, 5 to the third power. 8 is a perfect cube. That's the same as 2 to the third power. So the cube root of 8 is just 2. Cube root of x to the third is just x, because remember, x, this is the same as x to the 3 over 3, and 3 over 3 is 1. So x to the first power. And then your cube root of y to the second, you can leave it like that because you can't simplify it, the cube root of y to the second, or you can write it as just y to the 2/3. Either or. So 2x cube root y to the second or 2x y to the 2/3 is fine either way for me. All right, now number 17, 18, 19, 20, 21, 22. We didn't really go over this much, but I'll quickly explain it. So radicals with an even index and a negative radicand. So that means radicals like the square roots or fourth roots or sixth roots, eighth roots, an even index number. Again, square roots don't have the 2 there, but I mean, you can write it there if you want to. All right, these are even indexes. So any of these with a negative radicand. So for example, the square root is 25, right? That has 0 real roots because those give us the imaginary solutions. Those are imaginary numbers. The square root of that would be 5i. It exists, but it's not a real root. That's an imaginary root. So for these, any even index, it doesn't really matter if it's a square root or if it's a fourth root. If it has a negative number on the inside, it's still going to have 0 real roots. Okay? So that's just kind of one of those rules of thumb. Number 18, if you have an odd index, so something like the cube root, third root, fifth root, seventh root, any odd number index, it doesn't matter what number you have in here, if it's positive or if it's negative, it's still going to be 1 root, always 1 root, okay? So basically, for example, the cube root of 27 is 3. The cube root of negative 27 is negative 3. So the cube root has 1 root regardless, 1 answer regardless. So each of these are different, and they each have 1 root. It's just if it's a positive on the inside, your root is also positive. If it's negative on the inside, your root is also negative. Okay, because again, 3 to the third power is 27. So that's why, that's the answer to this. Negative 3 to the third power is negative 27. So that's the answer to that. They each have only 1 answer. Odd index always has only 1 root. Number 19, radicals with an even index. So again, back to square roots, fourth roots, sixth roots, whatever. And a positive radicand, so any positive number on the inside, those have 2 real roots. So for example, the square root of 25 is both positive and negative 5. Positive 5 and negative 5, because 5 to the second power is 25, but negative 5 to the second power is also 25. So there's 2 answers that fit in that problem. So it has 2 roots. So negative and even index has 0 real roots, odd index has 1, and even index and positive have 2. So following those rules, you can kind of quickly answer 20, 21, 22 without a calculator, because just notice what type of problem they are. Number 20 has an even index number, and it has a positive on the inside. So if it's even index number and a positive on the inside, I know it's going to have 2 solutions. The only answer that has 2 solutions is C. I don't even need a calculator. But yeah, it is 3 and negative 3, because 3 to the fourth power is 81, and you can check me if you want. Negative 3 to the fourth power is also 81. But I knew that answer only because it was even and positive has 2 solutions, and that was the only answer choice with 2 solutions. Right? A is only 1 choice, B is only 1 choice, and D it says none. So number 21 has an odd index. So I know it's only going to have 1 solution, because odd indexes have 1 solution. So it's not C or D. Now it's because of positive number on the inside, I know my solution is also positive. So it means A is the solution. So that's true. If it was the cube root of negative 216, then the answer would be negative 6, but it's a positive 216, so the answer is a positive 6. And the last one, it's an even index. Again, it's a square root, so that means square root of negative 64. Even index, but a negative on the inside. Even index with a negative on the inside means it has no real solutions, no real roots. Technically, the answer is 8i and negative 8i, but again, we're talking about real roots, not imaginary ones. So no real roots would be the answer. All right, now to wrap this up, let's solve these quick few little equations. So in number 23, we have the cube root of x minus 4 equal to 3. Now notice, all I got to do here, I can't really go inside the radical till the radical's gone. So I have a cube root. So if I want to get rid of a cube root, let me see if I can zoom in on this a little bit, make this bigger for you guys. There we go. I should have just been doing this the whole time. What are you doing? All right. Can I thank you? So when you have a cube root, the opposite of a cube root is something to the third power, raising it to the third power. So if I raise this to the third power, then that's going to cancel out the cube root. Of course, I need to do that on both sides. I can't just do it to one side, not the other. So when I raise the left side to the third power, it just gets rid of the radical, leaves me with x minus 4. And then the right side, 3 to the third power, is 27. And now it's just a normal equation. You add 4 to both sides, and we get x equal to 31. All right, let's scroll down a little bit. Number 24. So number 24 is a very similar process. It's just got more steps to it. So normal equation, again, anything outside the radical we need to focus on first. And so that's, in this case, the 5. We need to move this 5. It's a positive 5, so we're going to subtract the 5. And it's added, right? If this was a little bit different, if it was like 5 times that, I would be dividing it. But it's not times, it's 5 plus. So I'm subtracting the 5. That cancels it out. Leaves me square root of 2x minus 3 equal to 5. 10 minus 5 is 5. All right, now I can't go inside the radical till the radical's gone, so it's a normal square root. So the opposite of a square root is squaring, right? So I'm gonna square this side, I'm gonna square this side. So squaring the left just cancels out the radical, leaves you 2x minus 3. Squaring the right, 5 squared is 25. So normal equation at this point, add 3 to both sides. You have 2x equal to 28, and then divide by 2. And x will equal 14. All right, and one more. Number 25. So this is probably the hardest one on the test, but it's only hard if you forget how to do the first step. If you remember how to do the first step, then the problem's pretty easy. So the first step, notice we have radicals on both sides. Now, I want to get rid of these radicals immediately. So notice they're cube roots. To get rid of a cube root would mean having to raise it to the third power. Now, when I raise both sides to the third power, the left side is just the cube root. So the left side, the cube root is just going to disappear and be 4x plus 2. But on the right side, I get rid of this radical, but this 2 here is exposed. This 2 is also going to be cubed. It has to be cubed as well. The stuff inside the radical is not going to be cubed because it's inside the radical, so we're only going to get rid of the radical. But this 2 is on the outside. This 2 is going to get cubed as well. If you can remember to cube that 2, then you'll be fine. So 2 to the third power becomes 8. And then the stuff in the radical just doesn't have a radical anymore. It's just 3x plus 4, but no more radical. All right, but put in parentheses, though, because 3x plus 4 do go together. They belong kind of as one unit. All right, so at this point in the problem, you just distribute, combine like terms, and move on. So 8 times 3x is going to be 24x. 8 times 4 is 32. Bring this down. I'm going to move my x term over, so let's subtract 4x. That's going to mean 2 equals 20x plus 32. And then you can subtract 32. Now be careful, okay? People get this one wrong a lot, but 2 minus 32 is negative 30. Okay, and it's going to be a decimal, but that's okay. Divide by 20, and you can just leave it as 2/3 if you want. Negative 30 divided by 20, you can reduce that fraction, and x equals negative, oh, not 2/3, 3/2. Negative 3/2, or a negative 1.5 if you'd rather, okay? But negative 3/2 is fine. All right, that's going to be it, guys. I'm going to just wrap this video up so that you can move on about your day. Hope it helps. Good luck on the test tomorrow. I'll see you tomorrow. Bye.